Okay, hello again. So this problem says explain how to compute the dot product of two vectors. Okay, how to compute it. Then explain how it relates to lengths and angles. Okay. And then what about space-time and quantum mechanics? Okay, so don't be too scared of those last two. I'm not seriously asking you to do anything with them. But it's good to be aware of where this kind of thing comes up. Okay, so explain how to compute the dot product of two vectors, A. First let's just do an example. Let v1 equal 1, 2, 3, and v2 equal -1, 7, 0. Okay, then, obviously both of these are elements of R3. Then the dot product, sort of written like that, that's why it's called dot product. Well, first of all, it's a real number. It's not a vector again, so this is sort of weird. But yeah, so how do we compute it? Well, it's equal to, in this case, 1 times -1 plus 2 times 7 plus 3 times 0, which is -1, 14, and so it's 13 in this case. So these two vectors sitting somewhere in R3, maybe the first one is here, and the second one is here, and their dot product is the number 13. Interesting. And so what is this number? Well, it's positive. And so these two vectors would sort of point in somewhat the same direction. If this dot product were -13, then the vectors would be pointing in opposite directions, or at somewhat opposite directions. If this dot product were 0, then they would be pointing perpendicular, or 90-degree angle, or normal to each other. But anyway, those are just words. So in general, the dot product let V and W be elements of Rn. Then the dot product, let's write it a different way now, is equal to the sum of the VI's times the WI's. There's n terms in this sum, so it's literally V1 times W1. The first component's V2 times W2 plus the last term is Vn times Wn. And so when the vector's in R3, there's a term with 1, 2, 3 terms in the sum, and each term is a product of entries. So 1 times -1, add it to 2 times 7, add to the product 3 times 0. Okay. And so this is the same notation as V dot W. Sometimes it's, how else is it written? V bracket W, like this. This one is the one from physics and quantum mechanics. And I actually kind of like it more because this dot is bad because sometimes I like to write multiplication as a dot, and then this is a real number and this is a vector. And even just like 4 times 3 with a dot. So that's why I don't like this dot. I purposely made it much bigger. But again, this is just symbols. This is just notation. And no matter what you call it, this is what it is. This is the formula. It's a sum of terms. Each term is a product of the corresponding entries from the vector, like 1 times -1. Okay, so explain how to compute the dot product of two vectors. Well, I guess this is my explanation. Okay. And then B, explain how the dot product relates to lengths and angles. Okay, so V dot product W is equal to the length of V times the length of W times the cosine of the angle between them. So where theta is the angle between v and w. And what else is in this formula? Well, and then where v, like with this absolute value notation, this is like, you might have seen this as the absolute value of a real number, but in this case it just means the length. Like it's essentially the size. It's a way to say the size of this vector, and the size of a vector is defined to be the square root of the vector dot product with itself. So this, if we unwrap this formula even more, it's the square root of the sum of squares, vi squared. So, I mean, let's unwrap this even more. v1 squared plus v2 squared plus v3 squared if the vector has 3 components. If v is in R3. And same thing for w. I mean, just what's the length of w? Well, we define it to be the square root of the sum of squares. Sum of squares of components, or the coordinates or components of w. That's what it is. And what you can write it in all these different ways, and it's basically, I mean, what this says is that the dot product is somehow a square because the dot product of 2 vectors involves 2 vectors. So it's somehow like a square. And so to get the length, which we don't want to be the length squared, we want it to just be the length, we have to take the square root. And you also see this even in music, like the root mean square is maybe how amplifiers are measured, and all sorts of different things are root mean square. But root of the squares. Okay. Well, anyway, so now we know what every symbol is. We know what this absolute value of v means, or the size of v, or the size of w, which is also mostly said the length of v, the length of w, times the cosine of the angle between. And now, I just want to pause for a moment, because what's the angle between the vectors? Like, let's say there's vectors in 3D, and we have a vector here, and another vector, like, over here. What's the angle between them? It's not clear. I mean, in a plane, the angle between these 2 vectors is clearly that. Okay? In a plane, it should be more clear. But in space, what is it? Well, in space, you see that any 2 vectors, no matter what, even if they're in 18-dimensional space, any 2 vectors span or determine a plane. And so in here, you can imagine sort of this plane that, or it's almost like a tabletop. I mean, it's 2-dimensional. It's really 2-dimensional. Even if it's inside of R18, the span of 2 vectors is 2-dimensional. Well, unless they point in exactly the same dimension, and then they're just a line. But and in that 2-dimensional space, you just look at the angle. That's what it is. Okay, so this is defined. In other words, this is how they relate. The question asks, how does the dot product of 2 vectors relate to their lengths and the angle between them? And this is the answer. Okay. In particular, like, what if you want to compute the angle between 2 vectors? Well, then you'll compute this divided by v dot v, and w dot w. So this is a number, this is a number, this is a number, and we divide them. And that must be cosine of theta. So then you'd have to take, literally, in order to get the angle, you'd have to take the arc cos. Okay, so this is like the inverse of cosine, arc cos, or the inverse of cosine. So I'll never ask you to actually calculate the angle. The angle is something that we really can't calculate. Maybe what we can calculate is the cosine of the angle. Yeah, that's what we can calculate. I'm trying to think of if I did this wrong. No, I think I did it right. No, I did it wrong. Look at this. Okay, so this and this, those are different. Okay, and I often mess this up. Remember, the length of a vector is equal to the square root of the vector dot product with itself. Okay, and I often forget the square root. So in fact, we have to calculate 2 square roots to get even the cosine of the angle. Now what we can calculate, and this is what I was messing up, is if we do that, 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 then what we have is the square of the cosine of the angle. For cosines, they're just annoying to write, so this is the cosine of theta is a number, take that number squared, but people often just write the square right there. And I'm not sure why, but you should be aware of it. Okay, so this side, this left-hand side, we can compute just because we know how to multiply and add. We don't have to take any square roots. And so we can compute the squared cosine of the angle, but we can't compute the cosine of the angle exactly in an exact computation. We have to take some square roots, and then we can get the cosine of the angle. But then we'd have to approximate the square roots, most likely. And we can get the angle if we are then allowed to take the arc cosine, invert the cosine function, which again we have to approximate. Okay, I'm really going off track now that we have B done. Okay, so explain how, now what is the dot product on space-time according to special relativity? Okay, well, so all you do is instead of the sum of the squares, you just turn the last one to a minus. That's literally it. So I just wanted to point that out to you. If space-time were r to the 4, which it's not, but if it were flat, so or at least we don't think it's flat, we think it has curvature. But anyway, I'm not going to get into this. If space-time were R4, this is called Minkowski space-time. It's the space-time you learn about when you learn about special relativity in physics. You will learn about this space-time. It's clearly wrong, but this is what you learn about. And then the dot product between V and W is equal to V1 W1 plus V2 W2 plus V3 W3 minus V4 W4. Where the fourth component is thought of as time, and the first 3 components are thought of as space. Okay, so that's interesting. In particular, there are things that have dot product with themselves. This is the length of a vector. No, it's not, square root, okay. The length of a vector can be 0. In fact, that's what light moves in this way. It has length 0 in special relativity. So that's why we call the light cone or the null cone. So if you look up light cone on Wikipedia. Okay, let's look at the quantum mechanics one. Okay, so say we are interested, say we have a particle on or in one-dimensional space. Okay, I don't want to get into the physics. Okay, so let's just say in quantum mechanics there are wave functions. Wave functions are the vectors, which are vectors. They are vectors in an infinite dimensional vector space, not just Rn, but R like to the infinity, or R even bigger than that somehow. And the dot product between them, let's say V dot W, is equal to the integral of, let's say, V of x, W of x, dx, where x is in the space. Anyway, so think of, this is actually straight, it's like a sum. It's like a sum of vi wi, but it's infinite dimensional, so we take the integral. And for example, these can be functions on the real line. They can be complex valued functions on the real line. And actually one thing we have to do is take the complex conjugate, but if these are real valued, then you can just forget that. So it's sort of like this. Anyway, there's some things like C not R, and then actually wave functions aren't even really functions. They should be sections of a C-line bundle, And if you're interested, I can tell you more about my complete confusion about quantum mechanics, but my desire to learn more. And what I can tell you is that the dot product in quantum mechanics is a straightforward generalization of the dot product we are learning, but to infinite dimensional space. Infinite dimensional spaces. Now, there are certain things that are finite dimensional, like a qubit. That's quantum computing, for example, and that deals with finite dimensional spaces, but mostly it's infinite dimensional space. Okay. Yeah, so what do I want you to... The space-time thing I'd like you to know. You turn this into a minus. It's the same formula, almost. And then this thing, I'd like you to know that the sum of the components turns into an integral of the components. And the components here are the values of